Welcome to Math 31. We are looking at derivatives of trig functions. Today in Chapter 7, Section 3, we looked at the derivative of sine and cosine in the previous lesson. And in this lesson, we just extend it to look at all the other 4 trig functions and what their derivatives are. Here you have a warm-up question. We are wanting to figure out what is the derivative of tangent x, and we'll do it by finding the derivative of this quotient, sine x over cos x. So why don't you pause the video at this point, work through this question, restart once you have finished question number 1. You can pause now. All right, here. So what I get when I take the derivative of sine x over cos x, we have a quotient rule, low d high, that's the green part, minus high d low, again, derivative of cos is negative sine x, square the bottom, there you go. And as we collect some terms together, simplifying, we get a cos squared x plus sine squared x, Pythagorean identity, equals 1 in the numerator. So 1 over cos squared, which is secant squared x. There we go. And we could do that for all the other trig ratios, reciprocal trig ratios or quotient ratios. But what we figured out so far from yesterday's lesson, derivative of sine x is cos x. Derivative of cos is negative sine x, and we just discovered derivative of tangent is secant squared x. These 3 derivatives, you are expected to know they will not show up on the formula sheet. So those derivatives of the primary trig ratios. You will find these next 3 on the formula sheet, and we'll be using them in questions today, and so we'll just apply them when we get there. Let's look at a few examples. Question number 2, derivative of tan 3x. We'll need a chain rule because inside our tangent function, we have this other function, which is 3x. And so derivative of tangent is secant squared, keep the inside unchanged, times the derivative of 3x, which is just the 3 that I wrote out in front. Fairly straightforward. Well, let's get a little more complex using a product rule here. We have a product of 2 functions, and so we'll do the first function, x squared, times the derivative of the second function, which is secant x tan x. So that was up here, derivative of secant x times the tangent of x, plus our second function, which is secant x, times the derivative of the first, which is the 2x. We aren't asked to simplify, but for a number of these I will be simplifying. In this case, I'm going to pull out a common factor of x secant x, and then I have an x tan x plus 2 left over in brackets after that. Question number 4. Now we have a quotient. Quotient rule says we'll do low, which is tangent of x, d high. So this is one of the new derivatives. Derivative of cosecant x is negative cosecant x cotangent x, plus high d low, as we discovered in our warm-up question. Derivative of tangent is secant squared x. Square the bottom, there you go. Again, if all we were asked to do is just find the derivative, we could stop here, but let's do some simplifying, see where this takes us. I see this common factor of cosecant x, and both are negatives. We have a common factor of -1 also. So I factored that out. And then as I look at this tan x times cotangent x, remember they are reciprocals of each other, so they multiply together to give us 1. Now as you look inside this bracket, 1 plus secant squared x is kind of close to a Pythagorean identity, but if you look closely on your formula sheet, if you had instead a secant squared x minus 1, then it would equal a tangent squared. As it is, we can't replace this whole thing with a single trig function, so we'll just stop here. Which actually brings up one of the challenges. Because there are so many identities that relate one trig function to another trig function, how do you know when you're done? Well, there are many different forms that answers could have. We will just look for obvious identities and replace where we can, and otherwise we'll just stop the simplifying process. Well, why don't you try a few? We've done some questions together. There are a few check your understanding questions here, and I think the top of the next page. Yes. So why don't you work through these next 3 questions, and again, restart the video once you've finished to see my solutions. You can pause now. Cotangent squared x. We have a chain rule. Bring down the 2. Keep the inside function, cotangent x, unchanged, times the derivative of cotangent x, which is negative cosecant squared x. And I just rearranged the terms, not critical, but that's what I did. Question number 6. This is a fairly complex one. We have the product of 4x cubed times the tangent function, and then when we do the derivative of the tangent function, we're going to need the chain rule multiple times. We have tangent. Well, first we have the function squared, then the next layer in is tangent, then the next layer in is the 3x to the 4th. So here's what we have. First times the derivative of the second. Let me walk through this with you. For the tangent squared, I bring the 2 down in front and I keep the tangent function unchanged. So the tangent is the same, the 3x to the 4th is the same. Then I look at what's the derivative of tangent. Secant squared, keep the inside function unchanged, 3x to the 4th, times the derivative of that 3x to the 4th, which is 12x cubed. Then we have the second function times the derivative of the first. So as I do some simplifying here, I decided I would write this in simplest factored form. So there we have a 12x squared that's a common factor in that first set of products and then the second after the addition. Then there's also a tangent of 3x to the 4th that's common. Here it's squared, so we're going to have one left. And with all those leftovers, this is what we get. And that's far enough for simplifying. On to question number 7. This time we want the second derivative of cosecant 5x. So we'll begin, as we take the first derivative, we have a chain rule. So the derivative of cosecant is the negative cosecant cotangent. The 5x's stay unchanged inside the trig functions, but then we multiply by the derivative of the 5x, and that's where this 5 comes from. When we take the derivative again, now we need a product rule. So here is my whole process. Let's look at this line by line. My first function, negative 5 cosecant 5x, that's in green, that's unchanged, times the derivative of the second. Derivative of cotangent theta, let's call it, is negative cosecant squared theta. But again, it's a chain rule. We need it times the derivative of the 5x. We have another 5 in front here. Then we have our second function. Notice I kept this 5 coefficient in the front here. And as you probably noticed, and I'm just seeing now, if I'm going to keep, oh, there we go, this negative 5 as a coefficient of the second term, this sign here should actually be a negative sign. So in the green and red here, we have the second function with this -5 included times the derivative of the first. I'm just doing the cosecant 5x, and that derivative we already did. So that's this whole thing up there, and I just have that rewritten here in blue. So continuing on, having changed that addition to subtraction, I can have that negative times this negative over here, which makes it positive. So now it turns into addition. Similarly, in the first part, the negative here times the negative there makes this positive. So both products are now positive. And taking it a step further, there's a common factor of 25 cosecant 5x that I've pulled out to put it into a factored form. Again, we have cosecant squared theta and cotangent squared theta as part of a Pythagorean identity, but this is not the relationship. We can't replace them with a 1. So you can look at the identity sheet to see that there's not an obvious identity for us to apply there. Well, let's look at another example. This time, we have a point. We want to determine the slope of the line that's tangent to this relation. I call it a relation because x, y are mixed inside. Y is not explicitly defined in terms of x, so we're going to need to use implicit differentiation and then figure out where are we going to get, or what will we get for a tangent line at this point on that curve. So we begin by taking the derivative of the left side. This isn't the entire derivative yet. This is just the first stage. So what I did was I considered this square root as being brackets to the exponent a half, bring the half down in front, subtract 1 from the exponent, keep the inside unchanged. So that's the first layer to this derivative, and that's part of a chain rule. I think I'm going to need some space here. Now I need the derivative of the inside function. Well, the derivative of 3 is 0. The derivative of tangent of an angle is secant squared of the angle. But this xy is inside, or was inside, the tangent function, so now we need the derivative of x times y, which is a product rule. First times the derivative of the second plus the second times the derivative of the first. And the derivative of x was 1. So there we have the derivative of the left. Derivative of 0 is 0. I'm just going to shift this over. I couldn't remember how much space I needed. So now because we have these three things, the blue part times the green part times the red part equaling 0, each of these three parts, we're interested in what could make them equal to 0. So as I look at this blue piece, well, I have a negative exponent, which means I have my entire expression in the denominator. When can this equal 0? Never. Then for that middle piece, secant squared xy, when is this equal to 0? Well, a secant function is never equal to 0, because remember, secant is 1 over cosine, and so uh, the cosine, well, the 1 over cosine can never equal 0. And also, remember, we wanted to determine the slope of the tangent line. Neither of these two factors have a dy dx in them anywhere. So they're not going to help us figure out the derivative for this question. All we really need to consider is this red section. When is x times dy dx plus y equal to 0? And that's not a difficult equation to solve. Rearrange it, and we get dy dx is negative y over x. And we can plug in our xy ordered pair given in the question, when x is pi by 12 and y is 3, and simplify. There we go. There is the exact value for the slope of the tangent line for this relation at the point where x is pi by 12 and y is 3. Well, we finish off the lesson with a couple more check your understanding questions. Just before you get into the check your understanding questions though, take a look at question number 10 because I have made some updates from my original version of this question. So double check, you might have an x squared here. As I was working it through to do the second derivative, it was getting pretty complex and kind of tedious. So I took out that squared. So double check to make sure your question matches mine before you start question number 10. Tan y equals x times y. And we'll do the second derivative for that. So at this point, why don't you pause the video, work through these two questions, and restart the video once you have finished the two questions. You can pause now. Here's my derivative. Derivative of secant x is secant x tan x. Derivative of cosine x is negative sine x. So notice this subtraction sign changed to addition when I subtracted a negative sine x. Well, I can plug in the values that I have in the question when x is pi by 3. And we need to figure out some exact values here. Typically, we will want exact values, so don't go plugging things into your calculator to get decimal numbers. And we have secant pi by 3 is 2, tan pi by 3 is root 3, and sine pi by 3 is root 3 over 2. Simplifying that, we end up with a slope at this point of 3 times the square root of 3. We have a slope, we have a point, we can use the slope point equation of a line, plugging in the y value, the x value, and our slope is m here, and then I rearranged it into general form. Question number 10. We want a second derivative. So here is my work for the first derivative. Derivative of tangent y is secant squared y times the derivative of the inside function, which is a y, so that's times dy dx. And on the right-hand side, product rule similar to a previous question we did. So we have first function is x times the derivative of y with respect to x plus the y times the derivative of x, which is just 1. Well, collect the dy dx's to one side of the equation, factor it out, divide the bracket over to the other side, and there is my first derivative. So now as I come to finding the derivative of that derivative, I need a quotient rule. So here we have the low d high is dy dx minus high is just the y. D low is this whole green part here. So derivative of secant squared, I brought the 2 down in front, subtracted 1, and there I have the secant y times the 2, times the derivative of secant, which is secant y tangent y. So if we were to think chain rule, then this part is the f prime of g of x, and this part, oops, including that, is the g prime. So that was the chain rule. And then derivative of this x is equal to 1, so that's why that's subtracted at the end. Make sure you have these brackets around it because this y from the high, d low is this entire bracket. Square the bottom, there you go. Well, now we need to replace these dy dx's with this expression that we have here, the y over secant squared y minus x. So there's my next line. Just replacing the dy dx's. Well, that I shouldn't say just. That's not all I did. I also took this negative y that was in front of that bracket and I distributed it in. So there's the negative 2y, the negative y times 2, and that negative y times negative 1 gave me a plus y at the end. Well, we don't like having fractions inside of fractions. So since I have this secant squared y minus x in my numerator, well, in the denominator of my numerator, let's multiply top and bottom by that expression to get rid of these blue denominators. Here's what I get when that gets expanded. So let's think this through. This secant squared y minus x cancels out with this one, so I just have y times this bracket. So there's the y times the secant squared y, and then the y times the x being subtracted. So that is the first part. Let's just block that off. So that is from this part when we multiply that secant squared y minus x in. And then let's do yellow for this second part. When I multiply this in, here it's going to cancel out with this, but I'll still have this y. So this y needs to be multiplied into this whole thing, and so I'm going to multiply it to this y, and that's why we get a y squared here. But then we have this whole thing, whoops, here, that gets multiplied to this y that was by itself, and so I distributed that. Here's the y times secant squared y minus an x times the y, and those y's are coming from here. In the denominator, we also multiplied by this red part, so now I have an exponent of 3 in the denominator. We're almost done. For my final step, maybe I'll erase some things up here so we can see what I'm taking down. There wasn't much to combine here. The only pieces that I ended up combining together were this minus xy and this minus xy, which gave me minus 2xy's. And we'll do yellow again. This y, I guess that's green, y secant squared y. And here I have a y secant squared y. So I have two y secant squared y's. And then the middle term in here, that stayed unchanged. So that's carried through to the bottom. And that's as far as I went. No common factors to pull out. Well, I guess there are. There's a y I could pull out, but I just left it like this. So there we go. That's the end of this lesson. Time for you to do some practice in your textbook before we get to our final lesson for this chapter. Take care.